Our next speaker is a coworker of mine, Dr. Hojat Yeganeh. He's done several years of research into HDR specifically, and with the tone mapping operators, he's spent the last few years integrating his research into the Simplus algorithm, and he joins us today to talk about banding impairment detection. Welcome, Hojat.
Thank you, Chris. Thank you for your introduction. And thank you everyone for listening to my talk. So let me share my screen. I think you see, so if I do it like a full screen, where is full screen? Yeah, here, okay. So do you see my slide?
Yes.
Okay, good. So my presentation today is about banding detection or banding impairment detection. So I have few slides. I won't take too long time. I'm going to jump into the agenda for the presentation today. I'm going to start with the definition of banding and start saying what banding means and what's the definition of banding. And then after that, the reason that we see banding. So how human visual system works and responds to banding. I'm going to talk a little bit about dithering, so the technique that people use to reduce banding or mitigate banding. And then at the end, I'm going to show you one of the great achievement that we have in SSIMWAVE, and that is like a banding detection algorithm. So I'm going to show you the result of banding detection, and I will be more than happy to answer your questions if you have any. So banding, as you may know, we are living in a digital world, right? Everything that we receive, we need to digitize it. And when it comes to quantization and digitization, you usually lose information. And the same thing happens when we do compression. So not only the digitization part, but also the compression part can exacerbate banding. So banding is very annoying. It's very visible. And I'm pretty sure all of you have seen banding in recently, even like if you use OTT services. If I wanted to explain what banding means in a nutshell, you can imagine like a gradient, like a smooth gradient region, a big gradient region in your frame. If you compress that, first of all, if you digitize that, if you go to discrete part, you use some bits, like 8 bits, 10 bits, 12 bits, whatever, to make it digital or digitize that. And then after that, you because of the size of the video, usually you do compression. So as soon as you do these two steps, so you're introducing like information loss to the pixel levels, and then you may end up with some pixel levels that are meant to be represented uniquely if you think about the gradient shape. But those pixels will map to one like single or identical pixel values. So those things like creates, or that phenomena creates banding or contours. So then it will be very visible on the gradient on smooth regions. So it doesn't have to be a very wide region in frames to be perceivable, but in the wide region or in a very, very like noticeable gradient region like sky, the banding is very annoying. For example, I'm not sure how you see this frame, but this is one of the examples that I can provide in this slide to make it more clear, like the impact of banding or the visibility of banding. I know that Zoom can also do compression, but I introduced a lot of banding to this frame in order to be visible no matter what platform we are using. So if you focus on this frame, you see banding on sky. But I would say that we also have banding on road. So on paving, you see banding. And this is very annoying. Again, this is because of the compression and also digitization. So if you go deeper and try to understand why these two component like digitization and compression basically is introducing banding, it all comes to the contrast, the definition of contrast, and the way that human visual system works. So if you think about like an edge or a contrast, how we define a contrast in an edge. If you think that, like, if you focus on the box that I provided, so you see a very clean and clear contrast between the gray and white. The scientific definition of contrast, there are multiple definitions, but they brought like two important ones, which are very popular here. The first one is like if you take the difference of the luminance. Be careful, I'm talking about luminance, not pixel level. I will get back to this concept in the next slide, but for now, I just wanted to make it more clear that when we talk about luminance, we're not talking about pixel levels, like a 255 versus 254 or 253. We are talking exactly about nits or candela per meter squared. So if you have access to the luminance values of these two rectangle, like the gray one and the white one, if you take the luminance difference and then divide it on the average luminance of these two pieces or these two basically rectangles, then you come up with a kind of definition of contrast. So mathematical definition of contrast. There is another mathematical definition of contrast that is widely used as well. And that is like if you think about luminance of these two, like at the edge, and think about the luminance levels of these two different levels. If you take the max and then subtract the min and divide over the L max plus L min, then you would again have some sort of a notion of contrast. So of course, any sort of digitization, if you go to the discrete signals, there is no way of avoiding this, having such steps. So you always have these steps. But the question is whether I see this step or not. So whether the steps, because of the quantization, is visible through a human visual system or not. So this is an important thing. So the answer to this goes to the field of human visual systems. And you will be seeing a lot of things about contrast sensitivity function. So basically the whole concept of contrast sensitivity function is to define human visual system and the contrast, the different contrast for human visual systems under different circumstances and conditions. So that circumstances could be like a visual angle or viewing angle, or it could be background intensity. It could be anything like a chroma and the background chroma. So any sort of things like these, features or components can affect your contrast visibility, basically. So again, going back to the digital world, there is no other choice rather than quantization. So, and that quantization produces those edges and that edges, and the edge will be visible or invisible depending on the human visual system. So if we know and if we understand human visual system under different circumstances very well, then we can somehow penalize banding or detect banding, or we can decide and we can see if any sort of edge or jump or any like contrast is visible to human visual system or human eye or not. This is a curve that Dolby Lab provided in a lot of documentation that they introduced when they were talking about PQ functions for HDR. I'm going to use the same curve, but I'm not talking about HDR only or the banding impairment in HDR. I will say like more deep about why people see banding and SDR and HDR both, and what would be the mitigation or remedy basically for that, if there is any remedy for banding. So remember that I was talking about contrast sensitivity function. So the whole job of contrast sensitivity function is to say that what is the sensitivity of human eye based on or given some like certain circumstances. Let's say if I have a different background intensity values, 100 nits, 1,000 nits, 150 nits. If I show a pattern on that background, do I see the contrast, the visible contrast? If I see contrast, how evident or how visible that contrast is? Can I rate the magnitude of the difference or the contrast? So this is the starting point of this journey, basically, and the whole story about banding. And the way that basically people come up with 8 bits for SDR, and now they are talking about 10 bits or 12 bits for HDR, and also they're talking about PQ function. And when it comes to SDR, they're talking about gamma function. So what is happening? So if you look at this curve, this is a very, very famous curve. One of the famous guy, or one of the guy who basically plotted or fitted a curve, on a contrast or human visual contrast sensitivity function of a human visual system, or basically, let's put it this way, they have done a lot of subjective study on contrast sensitivity function. They have done a lot of experiments understanding how a human visual system works when it comes to different contrasts. So we have a lot of curves for that. We have a lot of experiments, but we also have some model. We have some basically mathematical model or closed form to fit those subjective data. One of the most important one of the most popular one is done by Barton. So the contrast sensitivity function of Barton is very famous, and these days almost everyone is using that. So when it comes to the contrast versus luminance value, so contrast versus intensity, or CVI, basically, we have this this curve. So that if you look at the dashed line, this is basically a threshold for the contrast sensitivity of human eyes. So basically anything, if you see any contrast that lies under this curve or this dashed line, so that means you don't see that. So if you're able to produce steps or digital steps or any like a discrete basically steps, but the magnitude of the steps or the contrast, basically, if the contrast step is less or below this dashed line, then you would not notice any banding or contouring, or basically you would not notice any significant difference between these two steps or the edges. You can imagine if I have 255, if you talk about 8-bit SDR, so you can think about 255 code words and 254 code words. If you use gamma function and then you translate these two code words to luminance, to the actual luminance value, and then you do the analysis, you see that the 8 bits for SDR gives you more or less something around this part. So which is, again, still below the Barton ramp, which is quite good. But again, there is no guarantee. These are all based on the probability, and it's not basically deterministic. Even all the experiments that people do for contrast sensitivity function. But anyway, so back to the quantization and the bits and the banding. So this dashed line is a key. So if you think about how Dolby basically came up with PQ function, what they did, they investigated the contrast difference. So they had like let's say 16 bits float ASUS, let's say HDR. They wanted to digitize that, and then they tried to do some math and calculation and see which one or how many bits basically gives us a very good curve or very good visibility or contrast, basically that can rely, or that relies basically under the dashed line if you compare it to Barton ramp. And then they came up with this, that they said if we use 12 bits and PQ function as a transfer function, remember that PQ or transfer function or gamma function that I'm talking here about, or you see it in the figure, these functions are good to translate code words to the actual luminance. So the whole thing about HDR, or the masterpiece that's hidden in the HDR, is this PQ function, the way that we translate code words to luminance or intensity values. So then people say that if we use 12 bits with PQ function, then we rely, or we are under this dashed line from Barton ramp, and then we shouldn't see any banding. Whereas 10 bits PQ, no matter what HDR display you are using, if it comes to PQ function, if it comes to 10 bits PQ function, you are above that Barton ramp. But does it mean that if we use 10 bits PQ, or when it comes to SDR function, if we use, SDR videos, if we use 8 bits, does it mean that we almost always see banding? The answer is no, because the banding is not, it's a function of so many things, and not only like the steps. The contrast masking is another thing that takes a lot of a role in when it comes to banding. The chroma part, like different chroma, the impact of chroma part is very different across the a different color gamut. So this, and remember, the whole analysis that people do, or they have done in the past, it's based on the contrast sensitivity function. And again, if we come back to Barton ramp, Barton tried to use that contrast sensitivity function, or all the experiments that people did in the past, and fit a model on the contrast sensitivity function. But remember, all the things that they've done, they've used luminance or intensity value. So when it comes to chroma, so and the color part, there is no, as far as I know, there is no reliable study that says that, hey, this is the contrast sensitivity of people or human eyes for this range of color gamut, or for this range of color gamut. And then you can come up with different way of, different way of digitization, or trying to find different maybe transfer function. So that is a very common thing. So again, go back to the curve, you see that the banding, the nature of banding is very simple, and that's why you start seeing banding everywhere, and no matter whether it is an SDR video or HDR video. If it is HDR video, even if it is 12 bits, if you think back, if you go back to this, even if you rely or trust this 12 bits PQ, because almost all the displays that we have these days is 10 bit, again, we are somehow sitting above Barton ramp. So no matter whether you're using SDR or HDR 10 bits or 8 bits, the contents are susceptible to banding. So what they do to mitigate banding, people, they know about this. This is a very known issue in the field for a long time. They know that banding exists in the digital world. But what they do, they do some sort of techniques called dithering. So they apply dithering to mitigate banding, or somehow fool people or fool human visual systems. So one of the important things, so I brought two techniques here. There are multiple techniques more than these two, but I brought two important techniques here. The one of them is applied in the grading suits. So when people, they are grading HDR content or SDR content, whatever, a piece of art, basically, or motion picture. This is what they call. So when they grade motion pictures, they apply this technique, and that is basically adding noise or film grain to the clean and smooth regions. At the end of the day, I think usually they end up adding film grain throughout the frame, or noise. But one of the most important purpose of doing this is to mitigate banding. So when you do have film grain, or when you do have noise in a very smooth region, or grading in a smooth region, you are introducing contrast masking to human visual system. Then when you do compression, when you do digitization, then you wouldn't notice banding that much, and the banding itself, or banding impairment, will not be very significant. The other technique that I brought up here is happening in the device side. So you may wonder how. the devices now, they are applying dithering, but this is a truth. This is a reality. If you buy a TV and then you connect your signal, or you're watching any video through the using the USB stick. So the TV applies, most of the TVs these days, they have a way to apply dithering. They are pretty smart now. And they apply ditherings. If you want to know if your TV is applying dithering or not, I have a recipe for you. You can just put like a video with banding. You know that you have banding. You have intentionally introduced banding. You encode that video, put it in a USB stick, connect it to TV, and watch it. And then you connect your TV to your laptop or whatever, or PC, using HDMI cable, and then watch the same content or decoded version of that content. And then you clearly see difference in steps or contours or banding. So TVs are pretty smart these days. They apply dithering. For example, one of the techniques that I brought up here is that they can play with the refresh rate and the pixel values. So and it's very popular in OLED TVs. On OLED TVs, because they have access or they have control on every pixel, then they can play with every pixel differently. And then they can play and they can fool the human visual system very, very easily by just playing with the pixels, like individual pixels. So the dithering is very common. Why? Because banding is very common. And these are the things, these are not the only two techniques that people apply for dithering. And there won't be these two techniques, or I think there will be a lot to come for mitigating banding. The well-known metrics, if you're curious to know whether I can catch banding artifact or not, we have tried multiple. It's very easy. You can go ahead and compute PSNR or SSIM. These are the well-known objective metrics that you can play with, and you can just run it against any content that you have. You can introduce banding. You can just run PSNR or compute SSIM or multi-scale SSIM or VMAF or even movie and the other well-known objective metrics. Because of the nature of banding, none of them is capturing banding impairment. So, and that was a very annoying impairment too. That motivated us, or this big problem basically motivated us to invest time on banding detection. And that's what we did. So we spent a lot of time on banding detection. And I brought up one of the examples here. So in the left-hand side, you see a frame with a lot of banding. And on the right-hand side, you see the result of our banding detection algorithm. One of the results, basically, we do report scores for banding, but at the same time, we do have a capability of producing a map, a so-called banding map. So if you look at the banding map, we are able to detect edges or the edge of the banding and penalize that. So that was one of the most important features that we recently came up with, and we are still trying to improve that. But we are very proud of having such algorithm in-house. I think I'm done with my presentation. I will be more than happy to answer your questions.
Thanks, Hojat. If anyone has any questions, you can unmute yourself, ask it, or if you want to just type it in the group chat, you can go ahead and do that. I have a few questions,
yeah, sure.
Hojat. So have you ever encountered any time where like banding would be part of the artistic intent of the video?
Yes, mostly in animation. So when they some of the animations, when they came up with just creating that there is an inevitable banding in it. So I've seen, it's very rare, but I've seen it. But the important thing is that, and it's very interesting that I've become seeing more like animations with film grain. So it's not clean clean animation. So I'm not sure whether you have had a chance to watch cartoons or animation these days, but because of my daughter, so I've had the chance to watch a lot of content at least once and look at the pictures or the frames. Interestingly enough, even for animation, I think they started to add film grain to it.
Interesting. We have a question from the chat. What other artifacts impairments cannot be detected easily with other common objective metrics, but Simplest can?
Well, it's a good question. First of all, I would say that all those metrics that I brought up here, like a PSNR, SSIMWAVE, multi-scale SIM, and VMAF or so, there are important drawbacks with them. The first thing is that they were designed for images, not for videos. But the second thing that I'm trying to focus more on this part is that the way that they have tuned or they have validated was against some of the subjective studies. So those subjective studies were mostly done using the old-fashioned videos or the videos encoded using the old standards. So I would say that there, even now, if you look in the literature or the publicly available data sets, you hardly see a very good subjective study done by people on, let's say, AV1 or VP9 even. So you can imagine as codec and as encoder basically are evolving, you see more different types of impairments. Some classical impairments are caught easily with these objective metrics, like a very heavy blockiness or compression artifacts or so. But when it comes to some subtle changes or new impairment, like this banding impairment, it's not new, but it wasn't part of interest for any subjective study as far as I know. So this is something that is the main drawback of these I would say classical objective metrics. The other thing is that again, you see a lot of newly artifacts when you use new techniques or new encoders. So these are the things. For example, recently we came across very interesting artifacts caused by H.264. So these are the things that we know for sure these metrics cannot catch.
We have another question from the chat. Jatin is asking, is Simplest banding detection algorithm a full reference or a no reference algorithm?
Yeah, it's a good question. The simplest banding detection algorithm is a no reference method. So basically, it's a no reference method.
I had another question. Would you still be able to achieve banding or see banding artifacts in very high bits, bit depths, like 24 bits per pixel, or?
Mm-hmm. So usually when it comes to the integer, so you know that when they capture raws like a movie or motion pictures, usually they captured in 16 bits float. So in that stage, I would say there is no banding. I haven't seen any banding at that stage. It's hard to see banding when it comes to 16 bits float. But when it comes to the digital, like this discrete word, and when they wanted to make it like integer values, then I haven't seen any 12 bits. I've seen 12 bits or one type of content in 12 bits on a reference monitor, but it's not for consumer. For consumer, you can't see 12 bits data. So even you transmit 12 bits, your display is not capable of showing 12 bits. So the display is 10 bits. So then in that case, I would say that I've seen banding no matter what bit depth I've used for the consumer TVs, which is mostly 10. So for 10, I've seen banding. For 12, I've seen banding. It's not that much. I haven't seen 24. I don't know whether that exists at all, but I haven't seen banding in 16 bits float by looking at TIFF.
We have another question. from Video Pro in the chat. Have you tried the banding detection algorithm on HDR content, such as HDR10 PQ quantized?
Yes, yeah. So it's a good question too. So we do have two versions of banding detection algorithm. So one for HDR and one for SDR. Yeah, for sure. So we do detect banding on HDR and SDR both.
Any other questions? I've posted a link to the video dev Harupu Slack as well. We also have a question about detecting with Adobe Vision as well.
Can you read the question for me, please?
Do we also detect banding with Dolby Vision encoded content?
Yes, yeah, for sure. So because we are able to decode Dolby Vision content, then we are able to detect banding on HDR, PQ function, PQ10 basically. So we are able to detect banding on Dolby Vision.
Oh, there's a follow-up question. The HDR, for the HDR one, I'm guessing the question is it transformed to SDR or is it done completely for HDR?
No, it's for the HDR. So we don't do tone mapping or any transformation from HDR to SDR to detect banding.
And I guess the question about what's the difference between banding and macro blocking, or can we detect the difference between it?
Yeah, that's a good question. So the banding and macro blocking in nature, they are pretty much, I mean, they are very same, right? They are very similar, but what is very different is basically the region, the shape of the basic contouring or banding, and the amount of region that they're being affected by this. So when it comes to macro blocking, again, it depends on the size of macro blocking, but usually the macro blocking, it creates some sort of a high energy texture. Basically, if you have a lot of macro blockings, sitting together, then it gives you some sort of a texture. But whereas the banding on sky, again, both of them, macro blocking and banding, they are the results of compression and digitization. But the banding, because we have because we have a smooth region and the smooth region shows banding, we have like a long contours or bands. When it comes to macro blocking, you usually see local macro blocking. You don't see like a connected blocks, a range of connected blocks.
Great. There's no other questions. A few more seconds. Okay. So yeah, thank you, Hojat. This is a great presentation.